big thank you to everyone at the Radcliffe. As you can tell from this lovely introduction, this has just been an enormously supportive and wonderful place in which for me to start this new research project. And I'm also really happy to have this venue to share with you today some of the results of this research, which I'll be presenting for the first time. So what I'd like to do is introduce you to the phenomenon known as the reproducibility crisis via a thought experiment. Let's imagine that we took a stack of recent scientific journals and we decided that we were going to look through them for articles that may help us develop new cancer drugs. Say we found an article that showed that cancer cells with a particular mutation were more sensitive to a particular drug. And we look through these journals, both some of the preeminent scientific journals in the world, as well as some maybe less well-known but still reputable journals, and we came up with around 50 articles that we thought might help us in developing new cancer treatments. Then we took those articles, took them to a laboratory, a well-equipped lab, full of scientists with lots of experience in doing this type of research, and said, just see if you can do these experiments again and get the same result. When you take that same cell with the same mutation and you treat it with a drug, do you also find that they're more sensitive, as was reported in the publication? So imagine the scenario in your head, and I want you to pick a percentage of articles that you think these scientists can probably recreate. In this scenario, what percentage of the findings do you think our laboratory scientists would be able to redo on their own? And I encourage you to pick an actual percentage here, just so you've got kind of a baseline in your head. This is very close to what happened in a real-life case where the pharmaceutical company Amgen in 2012 decided to publish their own experience with trying to recreate results from the published literature in their in-house laboratories. And in this publication, here is the number that they reported of the number of studies that they could reproduce in their lab. 11%, 6 out of 53 cases that they chose. This article generated a lot of attention in the biomedical research world, particularly in the leadership at the National Institutes of Health, and it became a historical turning point in what's now known as the reproducibility crisis, which is a trans-field phenomenon happening across scientific disciplines, as we'll see, where researchers suddenly are less confident that findings that they thought were stable could actually hold true on closer examination. So this article here was a moment when people really started paying attention to this. It shows up high in the citation list of key articles coming from leaders at the NIH when they decide to take action and introduce policies on reproducibility and rigor just a few years later. But one thing that's curious about this phenomenon is that in this article and in another article published by another pharmaceutical company, in this case Bayer Pharmaceuticals, what the researchers report is that the figure that they're showing us is in fact common knowledge. Okay? Here's what they say. It's the first article from Amgen Pharmaceuticals. On speaking with many investigators in academia and industry, we found widespread recognition of this issue. Our findings are mirrored by gut feelings expressed in personal communications with scientists from academia or other companies, as well as published observations. That's the quote from the similar article on Bayer. And these assertions here are not just anecdotal, they're supported by other kinds of data. If we take a look, for example, at a recent survey conducted by Nature Publishing Group in 2016, Nature asked 1,500 scientists from across disciplines whether they'd had any personal experience with failures to replicate, if they had had a case in their own lab where they experienced irreproducibility. And you can see here that the majority of scientists, in some cases the vast majority of scientists, reported experiencing a failure to replicate either someone else's result or even their own result. So this is not just something that pharmaceutical companies are telling us anecdotally. We also see in survey data that scientists have widespread experience with irreproducibility, sorry. And just as a note here, I'll pause to say that one of the things that's quite unique about the reproducibility crisis is that it's really reaching across fields here. Chemistry is maybe not the field where you would expect to see widespread irreproducibility problems, and yet it's high on the list. For the purposes of my talk today, I'm going to be focusing on preclinical research, which is research with animal models or cell lines, which is aimed, perhaps indirectly or distantly, but aimed at affecting human health. So that's the area that I'm going to be looking at, the type of research that the NIH funds, which is largely things with cell lines and animal models. So the take home here is it seems as though everyone has had experience with irreproducibility, at least that's what the survey data in Amgen says. And yet in this same survey, Nature also asked researchers, do they feel like this is a crisis? Almost all of respondents here said that they thought it was some degree of crisis. And in fact, you can see that about half of respondents feel as though it's a very significant crisis. So the puzzle that I would like to lay out for you today, and this is what most of my talk is going to be responding to, is the following one. How can irreproducibility be something that both everyone knows about and an emerging crisis that suddenly hit us? Maybe in other words, how could irreproducibility be something that is hiding in plain sight? If you think this through, it doesn't actually make a lot of sense that it could be both of these things at once. In that thought experiment that I asked you to do, my guess is that if you had a number in your head that was close to 11%, when I flashed the result up on the screen, it didn't really pack that much of an emotional punch. It seems like a true statement about the world. And you might be tempted to make an argument like, well, yeah, most research on the forefronts of our knowledge is going to be unstable. Science is a low-yield enterprise, as John Ioannidis, one of the headline figures in reproducibility, has said. But my guess is that if you picked a number that was substantially higher than 11%, say 50%, when I flash that number up on the screen, you have a completely different affective reaction. Then it feels more like a crisis, precisely because it doesn't align with your expectations. So this is the core of the puzzle here. How can this be something that we all know about and have experience with, and yet somehow this particular paper feels like a revelation where we realize something is wrong in science? In my talk for you today, I'm going to address this from two different angles. First, I'm going to approach this historically, putting the reproducibility crisis into the context of a longer history of clinical research reform, which is research with human subjects. So the results that we're talking about here in the reproducibility crisis, again, are those with cell lines, animal models, taking place in experimental spaces. But by putting this into conversation with clinical research, we'll see both how it is that reproducibility problems could be invisible and then suddenly visible. And then in the second half of my talk, what I'm going to do is combine this historical research with some ethnographic research to give us some purchase on new ways that we might begin to think about addressing irreproducibility today. In other words, the question of what does this history mean for the many people right now who are taking this problem very seriously and working to solve it. Okay, so I will turn now to the history of clinical research reform. If you read through this history, one of the things that you'll notice is that there are a lot of moments in the history of clinical research reform that bear a strong resemblance to where we're at today. Take, for example, Harry Mark's classic book called The Progress of Experiment. And he opens this book with a situation that sounds very much like where we're at right now in the 20th or 21st century. He says, over the course of research in the 19th century, researchers working in a variety of fields noticed a common problem. Individual observers, putatively studying the same phenomenon with similar techniques, gave divergent accounts of it. One of the examples that he talks about in his book is an early 20th century remedy introduced to help pneumonia. And this was one of these tricky cases where doctors reported different effects. For some, the serum seemed to work really well. In other cases, it didn't seem to be effective at all. And it was difficult to interpret exactly what this irreproducibility situation meant. Was it because the doctors who were using the serum were simply not accurately diagnosing pneumonia and therefore using it in the wrong patients? Or was it something about the drug itself, the serum itself, that was not working well? And what Marx argues in this book is it's exactly these kinds of concerns that lead to the development of the modern day system of randomized controlled clinical trials. The way that we now evaluate drugs for their effectiveness in these large clinical trials is born, Marx argues, out of this moment of concern about irreproducibility. There are lots of other parallels in this book between the kinds of problems happening in the clinical research world throughout the 20th century and the types of reforms proposed and what's going on today. But the story that I want to tell you is not just one that's about similarity. This is not one that's just about history reproducing itself, repeating itself. It is instead one about how it is that clinical research reforms actively make invisible problems going on in the lab and then suddenly reveal them. So there's a more direct connection. What I'm going to do here is I'm going to pick up where Marx leaves off. He ends his book here in the 1990s. And I'm going to start in the 1990s with a couple of historical events that show us how we get to this moment where we can have an aha moment about irreproducibility. The first event that I want to talk about in the 1990s is the rise of what's called evidence-based medicine, taking place here in the late 1980s and early 1990s. And the evidence-based medicine movement is born out of a concern that doctors are making clinical decisions really without respect to the scientific evidence, either because that evidence is hard for them to access, because it's scattered throughout the literature, or because they're trusting their clinical intuition more than they're trusting what's out there in the science. And so evidence-based medicine reformers then sought to try and collect, evaluate the strength of, and then compile scientific evidence for use by practitioners who are out there in the clinic treating patients. One good example of an organization founded in 1993 that probably many of you will have heard of is the Cochrane collaboration, now today just called the Cochrane, that does exactly that. It gathers up evidence for clinicians, tries to answer a meaningful clinical question and say, here's what you should do if you want to make your decision based on the scientific evidence. Now, it's important to note here that in the early days of the evidence-based medicine movement, this is a movement that's about collecting science and giving it to researchers. It's not a movement which is about critiquing science. And yet, the techniques that evidence-based medicine researchers use to try and compile this evidence ends up revealing systematic flaws in clinical research. How does this happen? I'll give you an example here, using this cryptic little graphic that's at the core of the Cochrane's logo. What this is it's a stylized image of what's called a forest plot. And a forest plot is a visualization of what happens when you try and combine the information from multiple studies or multiple clinical trials together. So to walk you through the information that we're getting from this graphic here, each of these lines here represents a different study. So say, for example, we found in our review of clinical practices that prostate cancer patients in one area of the United States are 8 times as likely to get their prostates removed in early stage cancer as patients in another area of the United States where physicians are practicing differently. And we, the Cochrane, say, okay, let's take a look at the available evidence and decide whether or not surgery actually helps early stage prostate patients. So we take all of the clinical trials that have evaluated this, and each one of these gets represented by this little box. The size of the box represents the number of patients in each clinical trial, and its spatialization on this scale here represents whether the outcome of the clinical trial showed that the treatment was effective or not. This middle line here represents the equipoise point, the point at which the treatment doesn't seem to do anything for people. So if your results are right in the middle, it doesn't seem to matter if you get surgery or not. If the boxes are leaning this way, that means that surgery did actually impact whatever our outcome marker was, say the number of years that these prostate cancer patients lived. And if it's leaning the other way, then that says that actually maybe the surgery harmed them. It might have actually reduced their lifespan because of the complications of surgery. So what this thing is here as a forest plot is it's a way of giving you all of that information about all these clinical trials in one graphic. And everything is summed up by this diamond here at the bottom, which is the statistical combination of all of those trials together. So if you want to know, what does the literature say? There's your diamond. But what I'd like you to notice is that this very same graphic doesn't just give you information about similarity, it also gives you information about difference. By comparing all of the clinical trials together in one graphic, now you can look at this and you can start to ask questions like, this clinical trial has much more strongly positive results than the rest. This one over here is leaning a little bit towards the negative effect side. And then you can ask questions like, I wonder what accounts for the differences in the outcomes between these clinical trials. For example, if I take a look at all of the clinical trials that have been funded by the pharmaceutical industry, do I find that they're leaning more in the positive direction? These are the kinds of questions that researchers within the evidence-based movement, the evidence-based medicine movement, then begin to ask. And asking these questions and producing the answers to them by the mid-2000s has started to reveal some very serious flaws in the system of clinical trials, particularly in drug development. So for example, one of the problems that this type of research reveals is what's called publication bias or selective publication. And the problem is as follows. Let's say you're a doctor and you're interested in prescribing an antidepressant. So you go and take a look at the literature to see what the clinical trials say about the effectiveness of the antidepressant. And you look and you see what's been published. All of the studies seem to indicate that it's pretty good. So you go home confident, thinking there is strong evidence for my use of this antidepressant in a clinical setting. But now imagine for a moment that all of the trials that showed negative results, where the drug didn't help people, or maybe it actually harmed them, those ones just haven't been published. They didn't make it into the published literature, or maybe they are just in lower tier journals where you're less likely to look. And in the mid-2000s, what we see is some revelations here of some instances in which pharmaceutical companies actively suppressed the publication of clinical trials with negative results, thereby creating a misleading impression of the efficacy of those drugs in the published literature. So this New England Journal of Medicine article tries to show you systematically just that, how it is that the effect size of this drug has been artificially inflated by having those studies with positive results placed in better journals and having the ones that have negative results simply not appear at all. And for those of you in the audience who might be psychologists or historians of psychology, one of the names that you'll probably recognize on this author list here is Robert Rosenthal, one of the founders of meta-analysis within the field of psychology. So you can see some fairly direct connections here, how it is that meta-analysis is leading through into this new research agenda, which is about probing difference. These issues here are not merely academic issues, they are issues that get a lot of attention within the popular sphere and within politics, particularly when Marcia Angell, who is the former editor-in-chief of the New England Journal of Medicine, where this article was published, writes this really scathing popular press book in 2004 detailing all of the ways in which she saw in her position as editor-in-chief pharmaceutical companies manipulating data in these ways in order to make their products look better. And this leads by the mid-2000s to a bunch of reforms, such as legislation requiring that pharmaceutical companies must register their trials in a publicly available database so that in theory you could go out and look and see if there were trials with negative results that were conducted but then never published. Okay, so the pharmaceutical industry is having a bad time in the first decade here of the 21st century because of these numerous scandals that have to do with the conduct of research. And that's not the only problem that the industry is facing. The second thing that's going on in the 90s, maybe more visible in the early 2000s, is declines in the productivity of the pharmaceutical industry. So in this image here, what you see is the number of new drugs approved each year by the FDA, plotted with R&D or research and development expenditure on the part of pharmaceutical companies. Now, commentators such as Marcia Angell have been very critical of this nice, neat curve here that you see on the R&D side, which they've argued is maybe kind of fictitious. But nonetheless, if we just take a look here at the molecular entity output, or the number of drugs being approved year over year, you can see that it's declining. Moreover, what you don't see from this graph is that a lot of these drugs that are being approved by the FDA at this time are what's called Me Too drugs, meaning they're very similar to drugs that exist already on the market, say yet another statin to treat your cholesterol, when we've already got a bunch of statins available to us. So the concern is both we're seeing a decline in number of drugs approved, and the drugs that are getting approved, they're not really breakthroughs. They're kind of incremental improvements on patient care, if they're really improvements at all. So this is an issue that is of great concern here, both to the pharmaceutical industry, obviously, but also to entities like the NIH that see it as their mission to try and improve human health, and it seems like something is going wrong here. The explanation that people give for what's going wrong is the following. The argument in the 2000s is that we have a translational research problem. We have good science going on over here. We've got clinical development partners over here. but we simply can't bridge the gap between them. If you take a look at this graph here in the context of the other information presented in the original article, what you'll see is that this graph is positioned right next to this other one here, which shows NIH grants and where the NIH grants are going. And the story, you can see just from the way that this is plotted, is that the NIH is giving all this money to PhDs, not to MDs or MDs PhDs, and presumably the implication is that by giving money to basic researchers, they're not really well positioned to be able to carry through the knowledge that they find into the clinic. Another way of illustrating this is with this nice graphic that accompanies the article, which plays on the term that the article uses called the Valley of Death. Nice, right? And the idea here is that you've got your bench scientist over here represented with test tubes and flasks. You've got your clinician over here with a patient. And this terrible rickety bridge is all that's connecting them. The argument here being is that we produce knowledge, it fails to actually make it over, and good ideas die in the Valley of Death. And this was an image that was used ubiquitously when I was doing fieldwork in the cancer community around 2010, 2011. This was the common and accepted narrative for what was going wrong. What's going wrong? We're not moving our knowledge from the bench to the bedside. And with this narrative in mind, the NIH invested quite a bit of money in the 2000s, in that first decade of the 21st century, trying to develop translational research infrastructure, trying to do things to solve what they thought was the problem here, this problem. Okay, so now we're in a position to return back where we started, to this Amgen article published in 2012, and to see why it is that somebody from the pharmaceutical industry was positioned to write this thing, and why it is that the NIH took it very seriously when it was published in the literature. In their article, Begley and Ellis, the researchers here from Amgen, actually only one of them is from Amgen, but that doesn't matter, what they're doing here is they're responding to a familiar problem about this lack of productivity in the pharmaceutical industry, but they're flipping the script a little bit, and they're positioning the problem in a different place. They're saying the problem is not translation, getting things from bench to bedside. The problem is that the science itself, that preclinical research, it's not good. There are systemic problems in that research. So it's a recognized problem, but it's a different way of formulating the problem, a way that most people had not thought of it before. Moreover, the pharmaceutical industry argued that it was in a really good position to try and see these flaws precisely because of all the scandals that they had weathered in the previous decade about the quality of their own research. So if the pharmaceutical industry had been getting hit hard with negative press about the way that it conducted its experiments, when it was looking across the hallway, so to speak, at the bench scientists and seeing the way that they did their research, they said, we see these same problems. So how is it that irreproducibility in the lab could be both widely experienced and sort of hiding in plain sight? Well, it was a problem that everyone recognized, but it was a problem that people assumed existed in a different place of the so-called pipeline. Everyone was thinking the problem was with the quality of clinical research or translation, not with the quality of basic research itself. So an accepted problem, but a really new formulation. Okay, so now what I'm going to do with this historical foundation in place is switch gears here in the second half of the talk and focus more on two lessons that we can learn from this history. And the first lesson that I want to draw out of this is that I think we really need better ways of talking about certainty or uncertainty in scientific information. One of the things that happens during the 90s with the rise of the evidence-based medicine movement is we see the proliferation of vocabularies and systems for trying to talk about the relative strength of clinical evidence. For example, probably many of you will have seen something like this thing, the pyramid of evidence, or the levels of evidence pyramid. This one particular one is taken from an evidence-based medicine published in 2000, but there are lots of variations that pop up in places elsewhere with slight tweaks as to what's included in it. But what this thing is really is a motivation or a way of trying to get clinicians thinking about the differential strength of the evidence that they're basing their opinions on, i.e., not all forms of evidence are created equal or should be treated as equal. So this graphic is trying to remind you, okay, randomized clinical trials are better evidence than, for example, an expert's opinion who's saying, based on my years of clinical experience, here's what I do. You should take that with a bigger grain of salt than something that comes from an RCT. So this is part of the development of a vocabulary for how to talk about degrees of certainty within the clinical information. A second example. This is a web page taken from the website UpToDate. The text here is not important. What I would like you to notice, though, is these little brackets that I've highlighted that contain these cryptic codes, grade 1C, grade 1B. What this thing is it's another kind of evidence-based medicine invention, again founded in the 1990s, which is a subscription-based service where doctors who are practicing in the clinic can go and quickly look up the best available evidence on a particular topic. So if you want to know how to treat a patient with a leiomyoma, you can go and see, all right, here is the evidence. What these things in brackets, though, are, when you click through on them, they're little notes about the strength of the evidence, and importantly here, to which kinds of patients the evidence applies. Recognizing that not all patients are similar, and a clinical trial that was done, say, in an older population may not actually apply to your younger patient who's sitting there in front of you. So with each of these recommendations within this text, grade 2B, grade 1C, you can click through and you'll see this is a weak recommendation. We see places where you might want to go against this in your clinical practice. Or this is a strong recommendation. Most patients should be treated in this way. So this is another example of a kind of vocabulary that clinicians are developing to try and say, all right, here's the relative strength of the data. Okay, now in contrast, compare that to the preclinical world, where there are relatively few or reasonably underdeveloped vocabularies for talking about differential certainty in your data. This is one of the things that I spent quite a lot of time studying in my first book here, Model Behavior, where I was in this laboratory with researchers who were using mouse models of psychiatric disorders, and they themselves saw, as Meredith said, all kinds of uncertainties in their own research. And so I was interested in, how do they communicate this then? How do they let you know that they're not entirely confident in what they're doing? Take, for example, this test, one which I spent a lot of time studying. It's called the Elevated Plus Maze. And it's a research setup that researchers use both in kind of basic research and drug development to study anxiety. What you do is you take your mouse, you put it at the center of the maze, and then you measure how much time it spends hanging out in these closed areas of the maze that have the high protected walls versus hanging out on these open platforms. Okay, very commonly used test. So how is it that researchers signaled their uncertainty about what was going on here and how much of a good test this actually was? They called it a test of anxiety-like behavior. Really rolls off the tongue, right? And I was really curious when I first entered the lab to hear people saying things like, well, in this test of anxiety-like behavior, or in this depression-relevant phenotype, and they would say that all the time, even when they were talking amongst themselves. Why did they do this? This vocabulary mattered to them because it inserted that little bit of uncertainty that what they were studying was not anxiety, it was anxiety-like. It seemed like anxiety, but it was not exactly the same thing. This vocabulary was one that worked quite well within this particular group of researchers who knew what they were talking about, but you try and take this vocabulary outside of the laboratory to communicate uncertainty to someone, and it kind of falls apart. No one knows what you mean. It just sounds like you're saying something overly complicated. And the journalist will say to you, can we call it a test for anxiety? And the scientist will sort of shrink. In fact, one of the hallmarks of the reproducibility crisis is the loss of the one common vocabulary that bench scientists and many others tend to use for expressing degrees of certainty, which is null hypothesis testing and p-values. These have recently come under fire from very prominent statisticians for being misused, overinterpreted, underinterpreted, and generally bad ways of communicating the degree of confidence that we should have in findings. So the point that I want to make here is that really the moment that we're living in, we have a lack of a vocabulary for dealing with or communicating uncertainty. What do we have instead? Well, in the popular press, what we have is a lot of conversation about truth. And truth is not a great language for talking about shades of gray, because truth, generally speaking, seems binary. We have truth, we have falsity. We have truth or post-truth. We don't have truthiness exactly. And so when these conversations are taking place in the popular press that are focused on truth, the idea that the truth is wearing off or that research is unreliable gives you the sense of crisis. It gives you the sense that something has gone wrong. There is no indication here that maybe we just need to downgrade our confidence in particular ways or particular situations. It seems like science has just failed, broken. And you can see from the images here of people falling through space, like the whole thing, the rug has come out from underneath of them. So truth and falsity, I think, a poor language for talking about this, and yet we do see practitioners attaching on to this very same language. Here's a group of scientists and librarians at the University of Utah who are doing a lot of organizing and infrastructure building around reproducibility. And what did they choose as their social media campaign hashtag? Make research true. You can tell what they're going for here, and yet the implication of this is, well, what is it now? False? So it's not a good vocabulary for trying to express degrees of certainty, and I think that this is one of the traps that we find ourselves in here with the reproducibility crisis in preclinical research in particular, is that that same infrastructure for talking about shades of gray in terms of our confidence, it doesn't really exist. Okay. The second lesson that I think is to be learned here from thinking about the reproducibility crisis in the context of clinical research reform is that we need a lot more attention to the dynamics of power within research laboratories. Now, if you put the history of reproducibility in preclinical research side by side with that of clinical research, one of the things that you're going to notice immediately, or that I notice, is that it's a lot harder to tell a good story about what's going on in the labs versus the story that I told you about the pharmaceutical industry. And that's because the pharmaceutical industry makes a really good villain in the story. So if you want to say things like, we have a problem of selective reporting here, you can tell an easy story about that. You can say, well, that's because the pharmaceutical industry really only cares about making profits and selling its drugs, and that's the reason why they're selectively reporting. Now, if you turn that around and think about the context of the laboratory, here it's a lot more uncomfortable because it's researchers themselves calling out other researchers on their practices, and because it's not entirely clear what the driving motivation is. So the problem of selective reporting in the basic research world, is that because of pressure to publish from funders, from your tenure committee, from journals who want to publish novel results? Or is it internal? Is it your own biases? And what you can see from this survey here is that in the various ways of interpreting whether or not this is an external pressure or something coming from within, people are tending to choose the external pressure narrative, pressure to publish, coming from somewhere else. And this makes a lot of sense, and I have some deep sympathy with the scientists that are trying to grapple with this, because in this particular case, it's like the call's coming from inside the house. So it's a lot harder to figure out how to talk about this thing. I want to pause here at this point here and give a shout out to my Radcliffe Research Fellows who are this year mapping with me this discursive space about the various problems that people identify and the solutions that they point to. And unfortunately, we don't have the data yet ready for prime time to show you, so I'm relying on this survey data instead. But we're doing a lot more work to kind of comprehensively map the things that people are pointing to as the sources of problems and suggesting as potential solutions. Okay, so externalizing narratives are kind of the fare of the day here. And yet, we have a large body of research that I've contributed to in science and technology studies on what the internal dynamics of the laboratory look like that we could draw on to think about some of the sources of the problems. For example, I'll take here a classic of laboratory ethnography. This is one of the first works where a sociologist, in this case, decided to go inside the lab and study scientific cultures as cultures in all of their richness. And conveniently for us, he focused on reproducibility. One of Harry Collins's key insights is that no two experiments are ever the same. And so in trying to decide what's similar enough to count as a replication, that's the place in which a lot of human judgment and human bias starts to creep in. For example, say you've got two researchers here, in this case myself and my little sister, on a family vacation looking fabulous. In many ways, we're quite similar. We've got the same haircut, we've got the same dresses and sandals, we were raised in the same house, but in some significant ways we're also different. We don't share all of our genetics. Perhaps we're working in labs that have different equipment. Perhaps one of us is a more skilled researcher than the other. So, are we similar enough for the purposes of comparison, or are we different in meaningful ways? That's a judgment where often culture plays in, because we tend to pay attention to some kinds of things more than others. Now, in the real-life case that Harry Collins was talking about, he was looking at early 80s experimentation around gravitational waves. And he was studying 2 different laboratories, one of whom had conducted an experiment and claimed to have found evidence of gravitational waves, and a second laboratory that conducted an experiment and said they found no such thing. And what Collins does is he looks at how the debate carries out and how it is that scientists try to decide what's real in this case and what's not. And he points out that this second experiment, this failure to replicate, is very unclear because it could be that they just didn't find gravitational waves. It could be that the experiment was also bad. Maybe their equipment didn't work. Maybe they weren't as competent experimenters. So it's not entirely clear how to judge this, and this is why the debate plays out for a long time. But importantly, the case that Harry Collins here is talking about is one where we have 2 high-status, well-funded labs who are trying to debate whose results should be taken as credible. This is not the way that irreproducibility presents itself most of the time. If you think about biomedicine and who does most of the research in the biomedical world, it's graduate students. And that power differential is something that we really need to take into account when thinking about how easy it is to recognize irreproducibility. So what I'm going to show you now here is a clip from a training video produced by the NIH, and this clip is meant to be shown to graduate students in the context of, say, a lab meeting to talk about irreproducibility in their own lab and how it is that they're going to address it. And I think this video will make pretty clear for you some of the issues of power differentials that I've been talking about. So I'll play this clip. It's about 2 or so minutes long.
I performed the experiment exactly as Donna described it in her protocol, and compared with her results, mine just aren't matching up. I just can't get the results to be statistically significant.
Well, something may be wrong with the way you're doing it then.
I guess.
This was the 4th protocol that Donna perfected when she was postdocing here in the lab. I mean, this is a good study design. I really don't get why you can't reproduce it either.
I'm following everything to the T exactly as described. It's just so weird that it won't work.
Well, let me ask you this. How many samples did you use?
I used 8 mice per group.
Let's try this. Add 2 more mice to each group. Then try a different statistical method. If I remember correctly, I believe Donna performed a 2-way ANOVA. See if changing those parameters gets you the results we're looking for here.
That's a good idea. Remember, Robin, toss out anything greater than 10. The normal range for living cells is 3 to 7, so anything higher than that is probably due to cell death. So keep that in mind. It could make a difference.
Okay. Thanks, Jamal.
And let me know how you do, okay?
Of course, Dr. Fielding.
Please call me Harry.
Dr. Fielding.
Hey, she's new. You did the same thing.
No, I didn't.
Yes, you did.
Oh, come on.
Oh, second scene.
Yes, whatever.
So, where are we here?
I did what you said, and I added the 2 mice per group, and look, it's still not statistically significant. These results are inconclusive, and they don't match with Donna's results at all.
And you varied the statistical test? Ran a 2-way ANOVA this time?
Yes. I mean, why is this happening?
Robin, I've been watching you a little bit in the lab here, and I hate to say this, but it seems like you're struggling a bit.
What?
Sometimes students come in here and just can't hack it in grad school.
It's just embarrassing that I can't repeat this test.
Well, I'm worried too. We do consistently high-quality work here, Robin. We just can't afford to lower our standards like this.
I'm sorry, Dr. Fielding.
Okay. So that's half of the video. In the second half, the PI realizes the error of his ways, that his postdoc, Robin, has been doing good science all along, does a mea culpa, and everything is resolved. But I think that you can probably imagine, it's a pretty reasonable hypothesis to assume that the story ends in exactly this place in a lot of other moments in history, okay? We can see here that there are power dynamics at play overlaid with race and gender that are really determining here how we interpret the outcome of a failure to replicate. This is a third way in which irreproducibility could be hiding in plain sight, that we're seeing irreproducibility and just misclassifying it as error on the part of the people that are doing the research. This is something here that we see a little bit coming up in reproducibility conversations. Obviously, I've taken this out of the NIH's own training guide, but it is not something that is as visible as it really needs to be. For example, if we take a look at the discussion guide that accompanies this video that the NIH provides for you to talk to your lab, they put their finger on precisely the problem that Harry Collins identifies. How do you know what normal is if you don't know the result? There's that interpretive space where human judgment is, where you're saying, is this a correct result or is this an error? Is this a true finding that there's nothing there, or is it simply that we didn't try hard enough to set up this experiment? So they've got their finger on the problem, but when it comes to actually talking about the power dynamics that would play into that judgment, here's where they really back off. This is what the question in the guide says with respect to Dr. Fielding's treatment of Robin. Do you think Dr. Fielding was too hard on Robin? Was there a more appropriate and effective approach that he could have taken when Robin was struggling to replicate Donna's results? So really, what's being ignored here is that the PI in this case wasn't asking him this question about what is normal and what's not. He believed that he knew already what the correct result was, the one that his prior postdoc had already published and that he had his name on in the literature. And he believed instead that what his graduate student was doing was simply error. And certainly he was likely to believe that because of the power dynamics of having the people on the front lines of science being the most junior people in the lab, combined with all of the race and gender overtones that are very clear in that video. This is something that I think that we urgently need to address because of the interpretive flexibility about the solutions that people are posing to problems of irreproducibility. So you remember the chart of solutions or problems that I showed you before. Here's its corresponding chart of solutions, again from this 2016 survey in Nature Publishing Group. And you'll see here that, in fact, teaching and mentoring make a prominent appearance. Better mentoring, supervision, better teaching, more time for mentoring, more incentives for reproduction, or incentives for better practice, rather. So there's a lot of things that are searching around this area to try and deal with this problem, but it matters crucially whether or not we think about the power dynamics inside of labs when addressing them. If better mentoring means finding ways to take seriously information that's coming at us from the people on the front lines of science, then great. That's something that sounds like it will help. But if better mentoring instead means just continuing to assume that new graduate students are likely to get it wrong and we need to help them find ways to get the results that we expect, that is not going to help your reproducibility at all. So this is something that I think we urgently need more attention to. Okay, so to sum it up, despite the fact that I have ended in not a very hopeful place, I would say, I'd like to emphasize that I think that the overall story that I'm telling is one that should make us feel hopeful. We've spent a lot of time over the years, rightly, looking at problems in clinical research within the biomedical community. And we can see irreproducibility in preclinical research not as a sudden emergent crisis, a thing that took us all by surprise and shows that science is losing its truth, but as a continuation of those reforms, an extension of the reforms that have happened in the clinical trial world and continue to happen, and that are now playing out in the laboratory. We're identifying many of the same problems. But this moment of reform is undoubtedly trickier to deal with. For one, it's more difficult for a community to look critically at its own practices than it is to look at a for-profit industry like the pharmaceutical industry and point out the problems. That requires some self-reflection, which is difficult to do. Taking these problems seriously also require talking about the power differentials within the lab, as I have emphasized here. And confronting that requires confronting the idea that science is not separate from society with all of its issues and social biases. It reminds us that science is done by humans and that we have to think about science as an activity embedded in society in order to make progress on these issues. And finally, thinking about how to talk about scientific data in ways that don't rely on the absolutist notion of truth, but instead emphasize those shades of gray, that's something that feels, again, deeply uncomfortable in this particular historical moment that we find ourselves in, where the idea of truth in post-truth politics seems to be up for grabs. So it's not easy, but these are issues that we can and should strive to make progress on, even if they're not immediately fixable. And the kind of research that I do is aimed at trying to tell narratives about what's going on that will help us more directly identify the problems so that we can spend our efforts in the places that I think really matter. Thank you for your attention. I would love to hear your thoughts on this material.